All right, so hi everyone, my name's Ian. I work for Google. I work at Google Plus, on Google Plus. I've been doing that for about 8 months now, so it's still slightly confusing and weird. This talk is about event stream processing, as you can guess from the title. It has quite a bit of code in it, and that's all up on that GitHub link. That's the joined in URL. Please do go and comment on there, not just for me, but for all the speakers you see. It's really useful for us because it tells us what we did right, what we did wrong. And it's also really useful for the organizers because it lets them say who really connected with the audience, the kind of things they should look out for next year, the kind of problems they should look out for. And if you want to ping me, ianb@php.net will get to me, or grab me on Plus or on Twitter. So, one small plug before we start. If you're interested in things like event stream processing, you may also be interested in messaging. And I wrote a kind of essay, tiny ebook thing. It's like about 80 pages over Christmas last year. It's on LeanPub. You can get it from that URL or just search for the title. And it's free. I would love for anyone that is interested in messaging or thinks they might be to take a look at it, give me some feedback. I've already had a lot of great stuff and I'll be updating it soon. So it's one small plug. So what I wanted to talk about was really a lot of things that have been of interest to me over the last few years. I've been looking at how you can do prediction from the point of view of machine learning and support vector machines, document classification, things like that. So build a model and then make a prediction based on it. And I started looking at messaging systems. I started looking at fire hoses and event-based systems and looking at how you could make decisions now. And what I got interested in was this concept of maybe combining the two in some way, trying to make those kind of decisions in near real time based on data as it was moving rather than data kind of in a bucket. We're really good at analyzing data that's in a bucket. We've got databases where you can do, incredibly complex queries, and you can do them very, very fast. Even a traditional relational database, your MySQLs and your Postgres's and all the commercial ones, you can, whack a bunch of SSDs and a lot of RAM in a machine, and you can do huge queries really quickly. If your queries are too huge, you can use Hadoop and things like BigQuery and all these kind of amazing big data tools we have, and you can process some seriously large volumes of data. And you can do that relatively fast. But it still takes time. You put the data into a bucket, you do some analysis, and you look at it. And then when you look at it, what you're almost always doing is trying to decide what you should do next. You're trying to make a prediction about how things are going to happen. So I wondered, could we take this stuff that we have with messaging systems, with queues, with real-time systems, can we do some of that analysis as it's going along? And that's the kind of idea that I wanted to look at and the kind of basis for looking at this talk. And I think you can. I think we have to think about data in motion. And we have to think about that motion in terms of the movement of events. And an event is real simple. It's just a programmatic representation of an occurrence out in the real world or in another system. It's a thing that has changed. And from my point of view, all an event is a tuple. It's a list. It is a list with some elements in it, A, B, C, that's fine. It could be a complex object. It could be a string. It could be whatever, but it's effectively a list. That's all we need to know about it to actually start doing things with it. But an event on its own is not interesting. It's a single record of a database table. There's not enough of it. Where we start getting interesting is when we think about an event stream. An event stream is just a series of related events. Now, they don't have to be related. You could have a sort of non-homogeneous event stream, but it's not so common, and it's not what we're really going to be focusing on here. So an event stream is the same kind of event, a series of them that has occurred over time or with some kind of ordering. Like a stock market price. So that would be the code for Exxon, and that's their price at various points. You can see that over time. It doesn't say anything about what that time is. It doesn't say anything about how that's been generated, just that there is a stream of events. When you have multiple streams of events that are related in some way, you have an event cloud. An event cloud is not just a set of streams, but a set of streams where there is some connection between them. So a stock market itself is an event cloud. If you think of something like a index. So like this is the price for the FTSE 100. What that represents is a series of streams of the prices of different stocks. And they're independent. You know, if one company goes out and does something amazing, then maybe their price will go up. If they do something bad, maybe their price will go down. But changes can affect all of the stocks in an index, some of them. It can cause some to go up and others to go down, and there's a correlation, there's a relation between them. So there's certain things you can extract, like if you have a bad economic outlook, maybe everyone goes down. If you have a index tracker, then how they work is by investing in stocks in rough proportion to how much of an index they make up. So if a stock becomes less valuable, makes up less of an index, then maybe that index tracker will sell it and buy other ones. And that causes a change. It causes a rippling change outwards. And analyzing these things is therefore pretty complicated. If you have a cloud of events, trying to extract useful things from them is hard, which is why a field called complex event processing developed. And complex event processing is a world of kind of big chunky services. Some are open source. There's Esper, which is an excellent open source project. You should check it out. Designed to do clever queries across a series of event streams. So you could do something like look for instances where an item has been placed onto a shelf. So it's been scanned on a shelf in a shop. It's gone out the door, which you've tracked with an RFID going through the door sensors, but it hasn't gone through a checkout, so it's been nicked. That you can do as a query, and you write that in either a kind of SQL-like language, or a lot of CEP systems you have a visual query builder, because they're just complicated. They're too hard for humans to reason about, to kind of easily code those kind of things up or do them in a more straightforward way. They actually need to drag and so you can see the flow of events to actually build queries. So these are, you know, big, generally expensive systems from people like Informatica and Tibco and huge names like that. And one of those systems was a company called Streambase, and this chap, Darek Ennis, worked there. And if you know the London Erlang or Java or these days Node communities or many others, you may have encountered Darek. He's a really, really smart guy, really nice guy. And he, when he left Streambase, started looking at the idea of event processing and complex event processing, and realized that for all the complexity in there, there's a good amount you can do with just a tiny bit of the work. You can kind of do a Pareto principle thing and say, I can get 80% of the ability to look at all these streams and do something with just 20% of the work. So he did that, and he built a little library on Node.js called EEP, Embeddable Event Processing. And what this was looking at all the parts of a CEP system, of an event processing system, and identifying what bits are straightforward to implement, and therefore what bits can we do really fast. Because one of the things Node is good at is asynchronous, callback-based, event-driven applications. It can do those really quickly. And he figured, if you can do something very, very fast, that's almost as good as being very, very smart. Simple things fast give you an awful lot of flexibility. So the things that he looked at were these stream operations, these basic things, these basic building blocks which we can use to start processing events. And those are pipes, the ability to move events from one place to another, move a stream of events over. They're maps, so that's a one-way transformation or a one-at-a-time transformation. So if you are taking an input value, you map it to something else. Maybe you augment it, maybe you transform it, and then you output it. So it's one event comes in, one event goes out. There's windows. These windows give you a view over a series of events and allow you to have some kind of calculation for more than one event at a time. And those windows, those calculations, those are either aggregate functions, which it's easiest to think of as kind of online functions, functions that update as they get new events, and sort of memory-based functions, things where we're looking at data that's been stored, which can be a thing like a join. So I really liked this library. I thought it was fun, and I thought, I want to understand it better. And I've got two ways of understanding something that work for me, and one of them is going and giving a talk about it, so this is that. The other way is writing it, actually writing code. So I ported EEP to React PHP in a weekend. This is not a complex code base, and you'll see this. And React is a really, really good project. It's basically a Node.js style, evented, callback-based system written in PHP. So you get to use pretty much the same programming model. And importantly for me, it had the pipes system, which Node has. And I think React is not necessarily that well known. So I just wanted to quickly show you what it's like to knock something up with that. So React is actually installed via Composer. And if you haven't used Composer, do. It's a wonderful little package management system, dependency management system. So what I'm going to do is just, oh dear. Let's call it server. So what I'm going to do is just quickly knock up a little React script that just shows the basics of what it is. Because it works slightly differently from how you normally implement a PHP process. So you normally would have some kind of web server calling out to either a running PHP process or sort of fast CGI or Apache and so on. But React actually is the web server. It's going to handle the connection for you. And at its base, React has an event loop. This is kind of the bit that you get for free if you use Node. Node really is an event loop. But with React, we have to build one. So we just create a loop like that. I mean, this is assuming I don't make any typos through this process, which is a low chance. And then we create a server for a socket like that. Now, at this point, we could plug that server into something else. Like we could plug it into an HTTP client and turn it into a web server. An HTTP server and turn it into a web server. We could not do a regular socket, so that is TCP, but we could as easily do 0MQ or another messaging system if we had a binding for that. To actually make it do stuff, we just say socket listen. So this is a TCP socket, it's just going to bind itself on port 4000 and loop run. And that just kicks off the actual process. So, assuming I haven't messed anything up, good. So we can telnet to it, and we can send stuff, but it doesn't do anything, right? All it's doing is sitting there listening, accepting collections, and being boring. But the really cool thing, and the reason React is excellent for this kind of work, is we have the ability to pipe events and streams through. So this is just like Unix pipe. You know when you use the pipe character in Unix and you can send all the output from one app to another one? It's really effective, it's really simple, and it lets you decompose a big program into lots of individual components with piping between them. So what we can do is do socket on connection. Because React is all callback based and event based, we register kind of a listener for an event. So this is saying there's a connection event coming in. That means there's a new connection that's happened. And then we implement a callback, which accepts a connection argument. And we can just do con, pipe, and we can send it where we want, like straight back out. See how that works? So then we can do hello world, and it echoes it back. So we've just piped the input straight back to the output, which is fine, that's useful. And that's happening very cheaply. If we were sending a 100 meg file through this, it's not going to like buffer it all and then send it on to the next step. As a chunk comes in, it'll send it through. It's just doing the kind of minimal work required to actually do that. And that means we can implement maps. So a map might be done as a function or as a new kind of stream type. So if I do something like this, then the through stream is something that has both an input and an output filter pipe. And we can connect them, and they go through the filter function. So we get some data, and we send it out again. So we can just return something like string to upper data. So all this is going to do is take whatever it gets in, string to upper it, and send it out of its out pipe. And we can do something like filter equals new upper stream. Use that. And instead of doing it straight to the pipe, we can pipe it to filter. And because pipe returns the last thing, the destination, we can then pipe that back out to the connection. So we could do that kind of infinitely. We can pipe as many other things through here. And this upper stream here knows nothing about where that data is coming from. If that's a 0MQ message coming in and being piped out to an HTTP connection, completely fine. So you don't have to worry about the kind of plumbing of your application when you're writing things like maps. And I'm not going to show it for every other example, but this kind of structure surrounds everything that we could do. We always have this flexibility to send data off where we need it, assuming this works. Good so far. So now it should be a shouty hello world. Yeah. So that is just happening as the data comes through. It's processing in that function and sending it back out again. Straightforward. So React is very cool, and React is exactly what you wanted to use. And that handles, because it's got pipes in it, it streams in it, and the pipes in it, it handles the piping. It handles the ability to move data about. So one of the 5 things we need is ticked off. Mapping functions, well, we've got all of PHP. It's a generic, general-purpose programming language. So there's almost nothing we can't do. We can go and look up in a database, or we can go and transform it in some way. We can do almost anything. So we don't need to be clever about the mapping functions. So they get taken away as well. So what we're left with is the windows. And that's roughly what EEP actually provides. So the first kind of window that's worth being aware of, and we'll look at 3, is a tumbling window. And this is really, really common use case. So you have events coming in. We have this stream of events up the top, 1 to 9 and then back down. We have a window size of 4. As events come in, they go into the window. Once it hits its limit, it emits, and it closes the window and opens a new one. So the window tumbles, and then we get a new one. Once that fills up, gets to 4, its limit, it emits and opens a new one. And the emit just means it's calling the function underneath. It's calling this aggregator. It's calling its memory function, whatever it is. So the kind of thing you could do with that would be, let's say, something like a server monitor. So you might want to take a stream of events from your server that are showing the latency, how long it's taken to serve a particular page. And you might want to use that as a alerting system. You might want to say, hey, my server's going a bit wonky. This is not a wonderful situation. So we can bring in autoload, and then we create a mean function. And the mean is an aggregate function, which is just going to calculate the average over the window. We create a new tumbling window with a size of 100, and we set up a callback in the emit event that says, just take that average that's come back from the mean function. If it's over 290, oh no, the server's not doing the right thing. We better signal alert. Just going to print it out. And down here, we actually pump data in. Of course, we're just making up data. So it's a win in queue. And in queue just says push that event in. So what that looks like when we run it is, well, kind of, what you'd expect. It's PHP example servermon. It prints out a bunch of alerts. So we pushed 50,000 events through it, and by chance, 50 were over that limit. 50 of them were events that would have triggered an alert. So we can handle quite a few events with this. The speed is quite good. And one of the reasons the speed is quite good is that these things don't keep a lot of data around. So if we look at the mean function, this is what's in it. It's that big. It's not complicated. But we're not keeping the whole window and going, count it all up, divide it. We're creating a running count. And just as that count goes, when we're told to emit it, we just emit whatever the mean is at that point. And when we're told to initialize, we just reset everything to 0. And the window actually manages it. The window doesn't keep that data around either. So what it's doing in this case is setting up a limit, and as events come in, it sends them through to the accumulator and forgets about them. When it's had as many as it needs, so when the index hits the size, it just tells the aggregate to emit. It just says, tell me what the current value is, and then resets it. There's very little complexity in it. And that's one of the things, the examples here are in this eep.php, but you could do them in almost anything, almost any stream system, almost anything where you can just write code. You can knock up this, literally, it's a weekend's work. So you can build something like that, but if you look at this, the average of something like detecting latency, it's not very powerful. right? Because I think it's Morgan Tocker that likes to say, if you look at the average temperature of people in a hospital, they look fine. You can't tell that some of them are overheating and dying and some of them are too cold and dying. So we can calculate more statistics. So what we've got down here is just the same thing, exactly the same thing, except we're using a slightly different stats function, all. We can calculate a whole bunch of different statistics at the same time, and all it costs us is kind of like a few extra variables. So we can calculate the standard deviation, which is how widely spread apart the values are. We can calculate the average, the min, the max. We can count up how many values we've seen, all of that kind of thing. So that means we can do a much more complex detector. We can say, hey, if the standard deviation is over this level, and the mean is over this level, and the max is over this level, then something really is going wrong. It's not just chance. And so we run that, and we get all the alerts we did have, and then I've actually saved the file. Then we get many less for the combined events. So the combined event is a much more sensitive discriminator. So we can easily start making more and more useful discriminators without having to change the data. We don't have to go back and emit anything new. We don't really have to care about going back and reprocessing old data because we don't care about old data. We care about things that are going to change now. So we can just update our detector, we can update our aggregate function, and we can do more interesting things with it. So the next type of window is a periodic window. And this is really, really important one as well, but also slightly tricky to use. So a periodic window has another concept, and that concept is the time. And a periodic window says the window length is not defined in number of events, but in the time over those events, which means it's very varied in how many events might be in there. You could have, in this case, we've got 5-minute window. We've got 5 events in the first window, 3 events in the second window, because there just weren't as many. The same time passed, but with less events. One of the things that actually happens with these kind of systems is you can find a lot of cases where it'll actually be an order of magnitude more events in some windows than other, because a lot of stuff is in fact spiky, is in fact bursty. So it can change how you're processing. That's why it's so important to keep as little data as you need, because it gives you the most flexibility as the data is moving through. You'll also notice I say wall clock. When I say wall clock, I mean literally the clock on the wall, the time that is on your watch or on your phone. That time is inconsistent. Anyone that's tried to deal with a bunch of servers and had to deal with NTP issues, there are times when your server goes back in time because it's got it wrong and it has to correct from NTP. So it doesn't mean that if the time now is this, that in a second the time will be 1 second greater. These things change. So you might not want to use the wall clock. You might want to use a monotonic clock, which is just a counter. You might want to use a vector clock, like Dynamo-based databases like React use. These kind of things are alternate ways of kind of measuring progress or some other factor which you will use to determine window size. And you can use them in a pretty straightforward way. So a similar sort of monitoring situation, maybe you don't want to monitor your server, you want to monitor the effectiveness of your site. So let's say that you have signups or you have purchases, and you want to look at, if I have less than a certain number in a certain time period, there's a problem. It doesn't even have to be with my site. It might be that my upstream bandwidth provider has a problem. It might be that my customers can't get to me for whatever reason. But it indicates that I'm not getting the usual traffic, the thing I expect. And the point of this is that all we're doing to do that is do a count over a window of time. So what the events are kind of doesn't matter. If I'm pushing through someone's bought this item event, it doesn't matter what's in that event for this particular window. So I can be pushing that for other reasons to do other analysis on and still make use of it to detect low rates. So doing this from a utilization point of view, same thing. We have an aggregate function, which is the count. All that's going to do is count up. It's pretty straightforward. And we have the periodic window, which has a size of 5 seconds, so 5,000 milliseconds. And again, we have an emit and that callback function that just looks at the count and say, hey, is it low? Is this a low rate? So when we do that, we can do examples low rate. And that's just going to sit there for 5 seconds. Now, we aren't having a clock go in the background. We're not having a kind of JavaScript style set timeout to say this is going to happen. We tick the clock when we want, because the clock isn't necessarily a wall clock. We could hook it up. If we wanted to hook it up to a set timeout and tick the clock every second, we could. But it's our decision. It's not something that the window decides. So you see there we had one low rate come in, so we signaled an alert. What the clock looks like is just a thing that ticks and tocks. So if we drop the size, I can actually make this a little bit bigger. So the clock has a couple of just simple functions in it. It just measures the time when it starts. It knows the interval that it has to tick over. And all it does when you check is just say, has the current time passed the interval? And that's it. That's all it needs to do. It doesn't need to know exactly how long has passed. It just needs to know, is it past the last interval? Because if it has, the window should close. So all the window has to do is tick it. So if we look at the actual periodic window, it just extends the monotonic window, because they're roughly the same. And all the monotonic window does is when you tick it, just says, has time passed? Tick. If it hasn't, carry on. If it has, enough time has passed for a window to close, then we tock it, which closes the window, we emit an event, and we start a new one. So periodic windows are really useful whenever you need to consider time as a factor for the window size. Not necessarily time as a factor for data, that's unrelated, but when you need to consider it for the actual window itself. The final kind of window that we cover here, now there's loads of windows that kind of CEP systems and event processing systems use, but so these are sort of the three most useful. And the final kind is sliding windows. So a sliding window starts like a tumbling window. Events go into it. When it hits the size, it emits. But once it's hit the size, it doesn't drop everything and start again. It just drops the first and adds the next event. So it slides along with the event stream. So once it hits its size, then every new event causes an emit. Every new event causes a window to causes the window to move on. And so with sliding windows, you can kind of do something that happens on every event. So you're basically, at this point in time, I look back my window size and I do some kind of calculation. So most of the examples thus far have been numeric data that we can do kind of statistical computation on, which is interesting, but there's lots of stuff that doesn't fit that. So we might want to do pattern matching. And all pattern matching tends to come down to finite state machines. So this is an example of a custom aggregate function. So this is not one of the sort of standard ones. This is one that defines a specific pattern. And that pattern it's looking for is a kind of stock market pattern. This is something that you might use if you were several years ago and not a very good trader. And the pattern is, you have a price, you see the price drop, and then you see it go higher. If you see that happen, then if in a short time you see a price and a drop again, you think, it's going to do the same thing, it's going to do higher. So if you see that tick, that's a pattern matched, and then you wait for a trigger of a drop, and then you know, hey, I should buy at that price, and it'll go higher, and I can sell it then, and I can make a little bit of money. So we can do that with a sliding window, because we want to look back. We just want the recent history. Has there been a tick in it? Has there been a tick and the trigger? If there has, I should do a purchase. If not, I should move on, and I should wait until there's the right conditions for the trade. And that could be easily modeled as a state machine. So we go from the state of not having anything to having a first price, then we see if it drops. If it drops, great. Then we wait to see it go higher than the original. If it goes higher, great. If not, at any point, we reset. And that's exactly what we do here. So as we accumulate, as new items get pushed into the queue, we just check the state. Which state situation are we in? And we take the appropriate action. So if we've not seen any data, if we're in the initial state, we just add a data item. If we've got that, we look for a drop. If we don't get the drop, we reset. And each state processes like this. Simple, straightforward code. There's no real data to hold, there's no real archive to look back. We don't have to physically look back across the window. We don't have to go back when we emit. We just have to update the state of our object as we go. So the tick detector can then just simply move through the states, and when the examples leave, so when the sliding window moves on, all it has to care about was, did the tick start before this window? So is the event that dropped the start of the tick? If it is, then we need to reset, because it's too long now. We've been waiting too long, it's no longer a valid thing. So we can run that just on some simple data, and we just use a sliding window with size of 7, and we're going to run it across this data with that tick function. So, okay, it just goes and it finds a tick. And it's not clear from that that it's actually doing something on every window entry. So if we just put in just a dot. So we see that those dots are just being emitted as the window closes. So it's a window of size 7, moving across, in this case, just 12 data items. And each time it moves, it's doing this test. It's saying, hey, are we in the right state? And only when it is in the right state does it emit. The rest of the time, it just bounces around the situations of the state machine. Again, not storing very much data, not doing very much calculation. So you can run many of these at the same time. You can process a lot of events very quickly. You can also do data that kind of is non-numeric at all. So this is, again, more numbers that we're processing with some rules around those numbers. But we can do the same thing with anything, really. One of the examples that Derek included in EEP.js that I ported over was Tim Bray's Widefinder. So Tim Bray, he works on identity at Google now, but he was formerly of Sun and one of the main guys behind XML. He was interested in looking at online processing of log files. So as new entries come into his log, he wants to calculate what's the most popular stuff on my site. So as stuff comes in, that just gets updated in a sensible way. And that's a perfect kind of problem for Windows and streaming systems. We don't want to look at the whole log file. We just want to look at it as it comes. So we can set that up, again, with a custom aggregate function. What we have here is a tumbling window of size 1,000. And we have that custom aggregate function for Widefinder. And what those 1,000 entries look like is like a standard Apache log file. You know, they're going to say the URL that was being addressed and the IP it came from and all that kind of stuff. So what we actually do in the custom function is use that regular expression to just pass out the URL and then just keep a count of matches. So all we're doing is keeping an array, and we make the URL the key into that array and keep a count for each URL we see. And then at the end, we emit that whole thing. So we see down in the callback, all it's doing is doing an array slice, taking the top 10 of them that have been sorted by the number of hits. So we can keep a running total of what's hot on the website right now. And that's very much what you do if you had a kind of e-commerce setup and you wanted to know what's the hot item right now? What's the interesting thing that's selling? You can keep a fairly limited amount of data in memory and still process events very, very quickly. So in this case, we have, as a test, the log file from Tim's site that he put up to accompany the post about this. And it's 10,000 log entries, and we've just batched them up into windows of 1,000. So it goes through them like this, and you can see in the earliest one, dynamic ID was top, and then atomic RSS was next, and in the most recent, dynamic ID is still top, and then something else. So you could see a current total of what things are going. And while this is hitting a file, we could do the same thing against, an actual log file that had data streaming into it, or just a pipe straight out of Apache or whichever log server we were using. So that's kind of the ability to look at numeric data and textual data and a lot of things. We can process events that make sense to us. But we can also consider joining between different streams and actually looking at some of this more complex interaction between streams. And that, again, doesn't have to involve a lot of memory. It doesn't have to involve a lot of time. So this is a SemiJoin across two streams. And this could be used, for example, if you're in a situation where you have a stream of auctioned items. So here's where items are listed, and a stream of closed auctions. So here's where the auctions ended. And you might want to look for the kind of items that people are just hitting buy it now right away on. Like, is there something about them? I just want a stream that within a window, an item has been added and bought. So they've gone really quickly. Fast-moving items, I can then look at them and say, oh, is it a certain category? Should I be promoting this? Whatever I want to do. That kind of decision involves looking at these two different streams and doing so in a quick way. But we don't need to care too much about the item. So a semi-join is like, well, a full database join would be like you have speaker ID and talk title and speaker name, and audience member name and speaker ID. And if you join those two together, you get all of those columns. If you do a semi-join for audience member to speaker, then all you'd get is the columns in audience member. You would only get them if there was a match in speaker, but you wouldn't get any of the extra data from the speaker. And that's exactly what we need here. We don't care about the data that was with the list auction event. We just care that it was there within this window. So we can use a very similar technique to the wide finder. Here, we just share an aggregate function between two sliding windows. So we create our SemiJoin function, and we create two sliding windows, and we have the same function shared. In order to make that work, we actually wrap the events in a muxt type. And all that does is just take the value and add a stream ID to it. So it's stream 0 or it's stream 1. That literally is it. There's nothing else going on there. And that's just so the function can tell where the data came from. And then in the SemiJoin, all we're doing is keeping two arrays. One for stream 1, one for stream 2. And obviously you could generalize this to as many streams as you wanted. And that allows us to see which IDs have been passed. So in the accumulate, we just check, is there an entry in the current array that says this item has been in there? If there is, we just increment it, because the same item might come up more than once, for whatever reason. And then we check the opposite array. So down here, we're just XORing to get the other stream ID. And we just check, is there the same ID in the other window? If there is, we set last value. And last value is omitted on every step. So if it's a match, last value gets set to something. If not, last value stays null. So we only get an omitted event if there was a match between these two streams. But we don't care what happened in the other stream. We don't care about what the data was. We just care that there was a match. And the compensate function is really easy, because we're keeping account of how many times we've seen a given ID. We can just decrement that count. Once it goes to 0, we know it's no longer within this window and get rid of it. So we're not storing a lot of data, just storing IDs and a count of how many times we've seen them. And we can run that, and we can put a bunch of data through it. Okay, so I just put 50,000 events through, and a whole bunch of categories came up that matched between these two things. So there's a simple way of joining those two streams and getting some results out. So finally, I just wanted to show kind of where you could go with this, though you want better code than this. This is really sort of a thought experiment in code rather than a particularly finished idea. And that was, it would be nice to predict the future, right? We'd like to be able to do predictions. And at the moment, that's difficult. Everything we've done gives us analysis, and we can make a decision based on it, but making a prediction is hard. But what we can do by looking at multiple streams is attempt to find a correlation. And if we can find a correlation over time, we can determine the leader. So imagine a situation where we had the latencies from a database and from a Redis server and from a web server. If we could look at that and see, when we see a spike in the database server, we see a spike in the web server 2 seconds later, then we could know, if we see that spike, we should immediately do some swim laning or turn off some features or do something to protect our user experience. So users never see the problem. So we can actually get ahead of the problem before it's visible to users. But we can do that without having to hard code, yes, this thing. If we see it here first, then here. We can actually continually watch the streams, watch the events, and detect whether there is a leadership relationship there. And all we need to do that is to correlate. So this really hacky class actually is a window kind of with aggregate functions in it. So what it does is create one window across two streams, and it divides it into sub-windows. So in this case, in the example, it divides it into 4 sub-windows. And then it compares each sub-window. And it compares them using a standard Pearson correlation. So this is just like if you Google correlate, the Wikipedia entry, the first thing in it is this formula. It's very, very simple correlation. And it's just saying, if it goes up in one, does it go up in the other? Or if it goes up in one, does it go down in the other? Either way, does one influence the other? And what we're looking for is a correlation between one in the past and one in the future. If we see that correlation, we know we've detected a leader and we can do something about it. So here we have some data there's a clear bit of correlation in there. We again use the muxing because we're putting 2 different streams together. And when we run it, we can see initially it wasn't sure. Initially it was a bit unstable, but then as the stream stabilized, we could see that we've clearly detected that stream 0 does lead stream 1. And that means we can make a decision about that. We could use stream 0 to predict the behavior in the future of stream 1. And that's really powerful. And if we didn't know, is this database versus Redis, database versus, we could just run the combinations. We have multiple of these running on different processes, different processors that allow us to handle this sort of volume of data. So I hope that gives you kind of an idea of some of the things that you can do with just some simple functions. I wanted to leave you with 2 quick points. One warning that you can process tens of thousands a second with this noddy code that's on GitHub right now. This will easily do 50,000 events per second. That's not a problem. That's not that big a number. If you are doing the same thing in, say, Darac's Node version, you can probably process millions of events per second. Now, the reason for that is that most of these examples don't do very much work. And if you're not doing very much work, you can do that faster in Node than you can PHP. If you're doing quite a lot of work per event, it doesn't make any difference. But certain languages are faster at doing nothing than others. And it's important to be aware of it, because sometimes you actually want to be able to do nothing really fast. So if you're doing this, I would imagine you can all get started right now with whatever you're using. It's just going to work. But if you really do get to a state where you're pushing hundreds of thousands or millions of events through a single process, not through multiple, where it's a different issue, but through a single process, you may need to consider which language you're doing it in. And I haven't tried this on hip-hop, but I would imagine it would be a lot faster if you did. So thank you. I think we're pretty much done on time, so I will be around. If anyone has any questions, please do come up and talk to me or ping me on any of those venues. Please leave some feedback on Joined In, and all the code from this is here, and all the code from Darac's Node.js implementation is here, and apparently he's working on Erlang and someone's working on a closure version, so there should be many, many language implementations of these same kind of ideas to look at. Thank you.